Assalamualaikum warahmatullahi wabarakatuh. My name is Nurwafia binti Khairul Tajuddin and my matrix number is 228948. So today my team and I will be presenting about our mini project, which is food operated trash can. So, as we all know, most trash can require people to lift the lid with their hands. This can be quite unhygienic, especially in places like hospitals, kitchens, schools, and also public areas where many people use the same bin. Germs can spread easily. So, to solve this problem, we designed a food-operated trash can. By pressing a pedal with your foot, the lid will open without using your hand. And then, a spring will closes the lid automatically after use, making it cleaner and more convenient. So, in this project, we use basic engineering dynamics principle to study how the mechanism works. We look at how much force is needed, how far the lid moves, and how strong the spring should be. And this project shows us how a simple mechanical system can help improve hygiene in daily life. It also proved that what we learn in engineering can be used to solve real-world problems in practical ways. So next, there are 3 Sustainable Development Goals SDGs that are aligned with our project. First, SDG 3, which is good health and well-being. Second, SDG 11, which is sustainable cities and communities. Lastly, SDG 9, which is industry, innovation and infrastructure.
So now let's move to the next subtopic, which is 4.1, design description. So the proposed design was a food operated trash can lid with a spring mechanism. So this design of a trash bin can reduce hand contact with a trash bin lid, and at the same time, this kind of design can improve personal hygiene and provide convenience to the user. And the main feature of this design is the foot pedal of a trash bin. The foot pedal is located at the base of a trash bin, and when the pedal is pressed down by the user using a minimal force, the pedal will lift up the trash bin lid and through the connected lever mechanism. So next, let's talk about the linkage mechanism in this trash bin mechanism. So the linkage mechanism also play a crucial role in this design. So the linkage mechanism consists of rods and levers. So the pedal is linked to the trash bin lid by a system of levers or rods that convert downward movement of the pedal into raising of the lid. So with this kind of mechanism, the lid of the trash bin can be easily lifted even by exerting a small amount of force. So next, let's move to the most important part of the design, which is spring mechanism. So an torsion spring will be attached to the hinge of the trash bin lid. So when we release the foot pedal, the spring exerts a restoring force that will automatically close the lid. So in this concept, the work and energy principle was applied. So when we press the foot pedal, we are doing work to compress or extend the spring. So that energy is stored as elastic potential energy, so which is later used to close the lid.
So I'll be talking about the kinematic assumptions for the trash can. So firstly, the mechanical components that are involved in these trash cans are the foot pedal, link, rods, levers and lid of the trash can. And we assume that these behave as ideal rigid body. So what does this mean? This means that during operation, these parts will now stretch, buckle or deform so that the movement given by the mechanism is correct. Secondly, we assume that the joints and pivots in the mechanism move smoothly without any rubbing or looseness. This means the part only rotate exactly as they should without any energy being lost because of friction or wobbling. In other words, the connection works perfectly and don't slow down or weaken the movement. For the third assumption, the whole mechanism is designed to move flat like on a single sheet of paper. This means all parts move only forward, backward, up or down. There is no twisting or side-to-side movement, and this makes it easier to understand and analyze how everything works. And the fourth assumption that we made is we assume the users press the foot pedal straight down in a steady and controlled way. So the speed and direction of the press stay constant, which help us easily understand how the pedal movement transfers force to open the lid smoothly. And lastly, the spring is assumed to work perfectly, meaning the force it pushes or pulls directly proportional to how much it stretch or compress. The places where the spring is attached doesn't move, so it always pulls in the right direction. We also ignore any loss of energy inside the spring, like friction or wear, to keep things simple.
So next, I will be presenting on our free body diagram of the foot operated trash can. So as you can see, on the pedal, there are two forces. One is going upward and one is going downward. The one is going downward is foot force when we step on the pedal. And then the other one is going upward, which is the normal force of the pedal. So moving on to the bin itself, we can see there are two forces also, which is one going downward is the weight of the bin, and the other one going upwards, which is the normal force of the bin. Next, we have the linkage force, which is going upwards from the linkage system. And lastly, we have spring force, which is going downward from our torsion spring.
For kinematic and kinetic analysis, we will be analyzing motion and forces in this spring-assisted pedal trash can mechanism. So the components involved are foot pedal, L-shaped rotating rod, bent linkage rod, trash can lid, and torsional spring. The assumed parameters are 30 Newton for foot force applied on the pedal, and the pedal arm length R1 is 0.05 meters, lid length 0.3 meters, mass of the lid 1 kilogram, lid opening angle theta is 80 degrees or 1.396 in radians. For the spring stiffness is 100 Newton per meter. Distance from spring to hinge or spring arm, R spring, is 0.08 meters. So from the assumed parameters, we can calculate the pedal moment, which is 1.5 Newton meter, and the moment of inertia of the lid about the hinge, where we assume the lid is a rectangular plane. Therefore, we use the formula 1/3 ml squared, and we will get 0.03 kilogram meter squared. For the spring extension, we will get 0.1117 meter, and therefore we can calculate the spring moment, which will get 0.8936 Newton meter. And we can thus calculate the net torque on the lid, which is the moment of the pedal plus the moment of the spring, and we'll get 0.6064 Newton meter. And therefore, finally, we can calculate the angular acceleration, where we uses the formula alpha equals to net moment over moment of inertia of the lid, and we'll get 20.21 radian per second squared.
So this is our dynamic simulation. First, let's see the video first. So as you can see, the video doesn't show spring, but our team added spring at the hinge of the lids. It is because we know that lid can open more than 90 degrees, so it is important to use spring to close the lid. If we don't use the spring, the lid will fall behind. For the reflection, this project allows us to apply dynamics concept to a real-life mechanism. Analyzing the trash can's pedal system helps us understand how force and motion transfer through linkage. Calculating moment of inertia, and angular acceleration gave us hands-on experience with rotational dynamics. We also learned how simplifying assumptions like neglecting friction make complex systems easier to model. Collaborating as a group improve our communication and task coordination skills.
So in conclusion, this project successfully demonstrated the design and analysis of a foot-operated trash can lid mechanism, offering a practical solution to hygiene concern in shared space by eliminating the need for hand contact. Through the integration of a spring-assisted mechanical linkage, the system enables easy touch-free operation and reliable automatic closure, making it both user-friendly and efficient. Applying engineering dynamics principle allowed for a true evaluation of the forces, motion, and mechanical efficiency involved, ensuring the design meets function requirements. Overall, the project not only depended the team understanding of real-world dynamics application, but also highlighted the value of teamwork and clear communication in the engineering design. Thank you.